Hello, I am Umang Mathur, and I'm here to talk about a novel linear time algorithm for detecting atomicity violations in concurrent programs. This is joint work with Mahesh Viswanathan, and both of us are at the University of Illinois at Urbana-Champaign. Even today, concurrent programs remain challenging to write. When a programmer has to reason about the correctness of their programs, they need to look at all possible thread interleavings. But the space of these interleavings can be extremely large. Consider, for example, this program with 2 threads. Each of these threads contain 10 statements, and as can be seen, the number of possible executions of this program is extremely large, making any kind of reasoning impossible. This is where atomicity can be handy. The basic idea behind atomicity is that code fragments can be assumed as if they will execute without interference from other threads, or in short, atomically. In the presence of such a property, the possible interleavings can drastically reduce. So in the same example, if the function foo and bar were atomic, then there are just 2 possible executions. One where foo executes completely first, and the other where bar completely executes first. Often developers mistakenly assume atomicity of some parts of their code, even though it may not hold. A classic example of this is the following. This is a Java program that implements a set data type using a vector. This interface ensures that there are no data erases on the elements of the underlying vector because all accesses inside the class vector are protected by a common lock. But when the add function in the set class is not atomic, then the program can exhibit unintended behavior. Specifically, when 2 threads try to concurrently add the same element to a shared set, then there can be cases when the vector has duplicate entries. So in short, race freedom and atomicity are complementary properties, and even if your program is race-free, there can be unintended behavior because of atomicity violations. So as we have seen, atomicity can be subtle to ensure, and concurrent programs can exhibit subtle atomicity violations. Can we detect atomicity violations automatically? Well, yes. There are some static analysis techniques that detect atomicity violations, but then these techniques report a lot of false alarms. There are also dynamic analysis techniques that check atomicity by analyzing program executions. And in this talk, I will focus on dynamic analysis techniques. And it is now time to talk about some technical details. I'm going to consider shared memory multi-threaded programs. These programs have threads and they communicate via shared memory. These programs can have other synchronization constructs like locks, but for the sake of this presentation, I'm going to simplify it and I'm going to just assume that we just have shared memory and threads. I will discuss a dynamic analysis algorithm, so I should be talking about executions. An execution or an execution trace of such a program can be visualized as a sequence of events. Every event tells you which thread performed that event and what was the operation that was performed in the event. So let's look at how this trace gets generated. In the beginning, the thread scheduler decides to schedule thread T1 and generates the begin event that marks the start of the code block intended to be atomic. Next, thread T2 gets executed and we see a begin event by T2. As you can see, the thread scheduler did not respect the atomicity specification of T1 and preempted T1 without completing the atomic block. After this, T2 gets evicted and T1 generates a write event on the shared memory location X. Again, the atomicity specification of T2 is not respected. Next, we see a read event on X. And this continues until we reach the end of the execution, which are marked by these end events that correspond to individual threads exiting their atomic blocks. Okay. So these 2 sequences of events that are marked by begin and end events are called transactions. And these are crucial to defining atomicity in an execution. So in terms of executions, atomicity corresponds to serial traces. A trace is said to be serial if every transaction runs to completion without interference from other threads. So as an example, this trace is serial because both transactions run uninterrupted. This trace is also serial, albeit with a different order of transactions. But if you look at this trace, both the transactions are interleaved by the events of the other thread, and hence this is not a serial trace. Well, while serial traces do satisfy this intuitive notion of atomicity that we're looking for, this notion is very strict, and no real-world program will meet such tight specification. This is why it makes sense to look at a more relaxed notion of serializability called conflict serializability. And it was first introduced by Flanagan et al. In their work that appeared in PLDI 2008. And this definition has been motivated from database literature. The idea behind conflict serializability is that while an execution may not be serial, it may be equivalent to a serial one. More formally, an execution is said to be conflict serializable if one can permute it to get a serial trace while respecting the relative order of conflicting pairs of events in the execution. Okay? By conflicting pair, I mean the following. Two events are said to be conflict with each other if they either belong to the same thread or they access the same memory location and not both are read accesses. Let us look at this trace. This trace, as you can see, is not serial. Now let's look at which events are conflicting in this trace. The begin event in T1 conflicts with the write X event in T1 because they're executed by the same thread. The write X event in T1 conflicts with the read X event in T2 as they access the same memory location X and one of them is a write. Likewise, there are other conflicting events marked by these green edges. We can permute this trace to get this trace, which is a serial trace, and moreover, this permutation preserves the relative order of every pair of conflicting events. Or in other words, no green edge is reversed, and this means that the original trace is conflict serializable. Now let's look at this trace, which is also non-serial trace. Now, if you look at the conflicting pair of events in this trace and the ordering of conflicting events in this trace, you will see that the only two serial permutations of this trace violate one or the other order of conflicting events. And thus, this is not a conflict serializable trace. Now, Flanagan et al. In their PLDI paper also presented a dynamic analysis algorithm, which until now was the only algorithm for checking conflict serializability. This algorithm is called AeroDrome Algorithmt, and it is a graph-based algorithm. As the execution is being generated, the algorithm constructs and maintains a graph. The vertices in this graph correspond to transactions in the trace. Now let's look at what are the edges in this graph. The algorithm places an edge from a transaction T1 to a transaction T2 if there are two events E1, E2 in these transactions that conflict with each other and E1 appears before E2. Okay, so when this happens, we say that the transaction T1 happens before the transaction T2. Let's see how this graph is constructed on our example trace. There are two nodes corresponding to the two transactions in the trace. Now the third event in the trace conflicts with the fourth event. And thus there is an edge from the transaction T1 to the transaction T2. Okay. Likewise, there is also an edge from T2 to T1 because of the conflicting events on the shared memory location Y. The graph constructed in this manner is acyclic if and only if the original execution is conflict serializable. And this is how AeroDrome checks for violations of conflict serializability. It stores the entire graph in the memory, updating the vertices and edges as new events keep getting generated. Each time the graph is updated, the algorithm checks for a cycle in the graph. Now, if we look at the graph constructed for a trace of n events, it can have order n nodes and order n square edges in the worst case. This algorithm therefore runs in time order n cube because it detects a cycle potentially every time a new event is seen, and each time a cycle detection operation takes order n square time. But a cubic time algorithm does not scale well in practice, especially for real world programs where the number of events and the number of transactions can be extremely large. So can we do better than this? Well, we sure can. And this is what we showed in our paper. So in our paper, we came up with an alternate characterization for checking conflict serializability, and an efficient algorithm called AeroDrome based on this characterization. AeroDrome is an online streaming algorithm that performs in a single pass over the trace and runs in linear time. AeroDrome leverages the power of vector clocks to achieve this. In practice, AeroDrome performs much faster than the state-of-the-art velodrome algorithm. Now, before we get into the details of the algorithm, it would be good to get an intuition behind what are vector timestamps. The idea behind vector timestamp is to track partial ordering on events, and it has been successfully used in distributed computing or in data race detection. Let's understand this using this example trace. So this has this trace has 3 threads, and let's say these blue edges denote some partial order of the events. Let us see how we can assign timestamp to these events. Okay? Every timestamp is a vector of natural numbers, which is indexed by the threads. And therefore here in this example trace, these vectors will have length 3. The timestamps will be such that the point-wise ordering on timestamps reflects the partial order we want to capture. So here, for example, initially the timestamp of every thread has a 1 in its local index and 0 everywhere else. As we see new events, we can assign timestamps to these new events. So in the beginning, the write X is performed by T1 and it gets the same timestamp as that of T1, which is 1, 0, 0. Next, we see the write of Y, which is the second event in T1. So we increment the local clock and thus assign the timestamp 2, 0, 0 to this event. Now, after this, we see a read X event in T2. The second component of its timestamp is 1 because it's the first event in T2. Its first component is 1 because it is ordered after the write X event in T1. Now we can assign timestamps to all other events in a similar manner. The timestamp of the last event write Z is obtained by using the timestamp of the 2 earlier events that preceded according to the partial order. Timestamps are particularly useful when we want to check for reachability between events. And this corresponds to a simple point-wise comparison of the timestamps of these 2 events. Now, when it comes to checking conflict serializability, coming up with an algorithm to assign timestamps is not trivial. And there are several challenges that need to be overcome. First, conflict serializability is defined in terms of happens before ordering on transactions instead of individual events. And assigning timestamps to entire transactions is a difficult task. So how do we go about it? Well, the first insight we have is that we can assign these ordering on individual events and use these event timestamps to check for violations of conflict serializability. Okay, so with this idea, let us look at this trace. This trace is not conflict serializable. And in terms of event orderings, there is a path using conflicting orderings that start in the first transaction, visits the second transaction, and goes back to the first transaction. Now, if this happens, clearly the 2 transactions cannot be scheduled atomically because doing so will violate some conflicting order. This leads to our first conjecture criterion for formulating conflict serializability in terms of event orderings. And since this ordering is a partial order, there is hope that we can get a vector clock algorithm for it. Okay, so let us see if this criterion works beyond one example trace. For this, consider this trace. This trace is again not conflict serializable because doing so will violate one or the other conflict order. But here, there is no such path of conflicting orderings that starts and ends in the same transaction. And this means that this conjecture is actually wrong. In our paper, we actually discuss many more such challenges that one needs to overcome in coming up with this kind of an algorithm. So we finally formulate one particular ordering, which we denote using the symbol less than E. And this ordering captures conflict serializability. The precise definition of this order is very technical, and I encourage you to read our paper. The characterization of conflict serializability using this order is rather simple. So it says that there is a conflict serializability violation if and only if one can find three events, E, F, and G, such that E and G belong to the same transaction. F belongs to a different transaction. E is ordered before F according to this new order less than E, and F is ordered before G, again using this new order. Well, with this, let us look at some details about the algorithm, which we call AeroDrome. The complete algorithm is very technical and is presented in a paper. The key idea behind the algorithm is to capture this new order less than E that we've defined. And we want to capture this using vector timestamps. In particular, the algorithm assigns timestamps to events so that the point-wise ordering on the timestamp is isomorphic to this less than E ordering on events. Now, let me talk about some high-level aspects of this algorithm. First, the algorithm runs in an online streaming fashion and does not store the events in the entire trace. It assigns timestamps to events as they get generated by the underlying program. Further, it does not store the timestamps of all events, but only the timestamps of a constant number of events in some vector clocks. The algorithm updates these vector clocks as new events are seen. An AeroDrome detects conflict serializability violations as they occur, again using vector clocks. In terms of algorithmic complexity, the algorithm runs in linear time and uses constant space, assuming constant number of threads, locks, and shared memory variables in the trace. Now, we've implemented our algorithm in our dynamic analysis framework called Rapid, which is available on GitHub. Rapid is written in Java and facilitates comparison of different dynamic analysis algorithms for concurrent programs. In our evaluation, we used traces generated by this other tool called Roadrunner and compared both the algorithms, Velodrome and AeroDrome. Now let us look at the highlights of our evaluation. Again, please take a look at the paper for complete evaluation details. We use some standard Java benchmarks that are prominently used in the race detection literature. We generated traces using these benchmarks and ran AeroDrome and Velodrome on the same trace for an apples to apples comparison. The trace sizes vary from a few hundreds to over 2.8 billion events. And we ran both Velodrome as well as our algorithm AeroDrome on the same traces and set a timeout of 10 hours. The graph-based cubic time algorithm does not finish on many of these large benchmarks. On a majority of the benchmark traces, we see that AeroDrome has a non-trivial speedup, demonstrating the power of a linear time algorithm. With this, I'd like to conclude by summarizing our work. We came up with a dynamic analysis algorithm for checking conflict serializability, which is a popular notion of atomicity in concurrent programs. We came up with an alternate characterization of conflict serializability and an algorithm called AeroDrome that checks for conflict serializability violations using this algorithm. This algorithm is a one-pass online streaming algorithm that works in linear time and uses vector clocks to get the speed up. Our evaluation shows the benefit of a quadratic speedup of AeroDrome over prior state-of-the-art Velodrome algorithm. Now, an algorithmic improvement in such a fundamental problem like checking atomicity violations opens up a lot of avenues for future work. First, there are several applications of this result. This includes speeding up of model checking algorithms for finding atomicity violations in programs. Next, recently there's been a renewed interest in predictive race detection, and most advances in that area are driven by vector clock algorithms. And we hope that our vector clock algorithm for atomicity violations can lead to fundamental innovations in predictive atomicity violation detection. Finally, there are lots of avenues to further improve the performance of our algorithm to make it more ready for practical deployment. These include algorithmic optimizations like the epoch optimization popularized by FastTrack, Further combination of static analysis and synchronization protocols can also reduce the runtime overhead of this algorithm. With this, I'd like to thank you for listening to me.